Pudong, anyway, you can discuss with that. But leading discussion, I think you show something important or tell us something we have to pay special attention to it. And we can discuss together and have some questions. Okay, your time anyway, good.
Okay. So we will start from the very beginning and solving some linear equation first. And so let's consider the following problem. Can everyone see my notes?
I think I can see you.
Okay.
Yes, we can.
So we will focus on the following equation. Qt plus omega so this is a general evolutionary PDE, linear PDE with constant coefficient. Omega is a polynomial. And the Fokas method can solve the initial boundary value problem of this kind of evolution equation in general. And there's a couple, so there's initial data, Qx0 equal to Q naught x. So this is called initial data. And we have boundary data, boundary values. So for the initial data, there's three cases: whole real line and the half line and the interval. And the boundary value, Qx, no. We have dxj q0t as gjt. So you can post all the way to the n-1 derivative. So here we have the degree to the nth degree, so we can post the boundary value all the way to the n-1 derivative. Or you can post on, so this case is for the whole real line. If it's not a whole real line, you can post more boundary conditions because you have more boundary.
Here,
so,
no, here I just got a question. You see,
yes.
For the boundary value, right? Boundary value, so we can choose some other derivative, for example, from 1 to the nth order derivative at the boundary. So this is will be new boundary value problem. I think it's still solvable, So actually, we have a lot of problem to work out actually, right? This is a new problem.
No, here it's just a classic definition of the initial boundary value problem. Of course, you have a Newman problem.
The other boundary value problem still workable, I think. You
This
choose
one,
boundary value from J from 1 to n. Still solvable, I think.
no,
folks, they don't solve this kind of boundary value problem. So the boundary value, if you want to raise a well-posed boundary value problem, it's hard. That nobody can tell, particularly for the nonlinear. Oh, this is linear.
Yeah, for linear, it's well defined. I mean, it's not too hard to post a well-posed problem. You only need to give a
linear. What kind of boundary value is well-posed? Can we raise the boundary value from J from 1 to n?
No, you can only you just pick 1/2. Take the integer. You only need those information to well-post a problem on the whole real line. I mean, it's I'm trying to avoid discussing the well-postedness because
well-postedness is very, very difficult problem. So here I'm thinking.
No, for linear problem, it's very simple. But we are not going to discuss this.
For linear problem, even for linear problem, it's not a simple.
For this one, for this evolutionary equation, it's well developed, so no problem.
Who developed this kind of theory?
Yeah, this.
Who developed?
Mhm.
I don't think it's well developed.
Um,
For the third order boundary problem, no text.
no, this is very simple because it's a constant coefficient linear PDE. It's
Even
like
constant. For example, for example, for the wave equation. So the boundary value problem, it's hard for guarantee the uniqueness solution or wave post. Even the UX, your TT equal to UXX, boundary value problem is diverse.
yes, but
So it's
there's
not
many
clear. It's not
many
clear
theorems.
which kind of boundary value problem will guarantee the wave postness. I don't think this is the first. This is the evolution equation. So
Yeah,
a little bit
very
easy
simple.
because first order. Actually, for this kind of equation, the general solution can be presented, no problem. Yeah, so we don't need to solve actually. Any solution we can present. Very simple.
No.
So for the linear, this is even the linear, not even for the linear first order quadrilinear, the general solution we can present. Only this kind of equation we can present. This is in OD, in any OD textbook. Pretty last chapter, I think we'll talk about first order partial linear different equation, and we can present the general solution. No problem. You check the textbook of OD published by Beijing University. The last chapter is about this kind of PDE. How can we determine the solution? We can determine general solution. So for the linear different equation, we don't have the general solution. So we can determine general solution by the Lie method actually. Anyway, go ahead.
Okay, so if you have more boundaries, you can put some more boundary conditions. So for this one, if you have on the interval, then you can post on the, so in the phase space T X, if you consider interval, then you can post the boundary condition on this this way. So here, and so this is a general concept about the initial boundary value problem. And now we are going to solve those problems by examples. So example 1, let's solve the, let me think which one is better.
The both boundary value at 0 and L from G from 0 to N minus 1?
No, I mean, you cannot post all the, that's overdetermined.
Okay, that's overdetermined. Right.
Yeah, but so like, for example, no. For the whole real line, then you only need the one, so this case, you only need 1 plus 2. And 2, you only need n over 2 conditions. So here you have n conditions, but you only need half of them to get a well-post problem. And if you have more boundary, then totally you need n. For if you have 1 plus 2 plus 3, then you need the n boundary condition.
What do you mean 1 plus 2 plus 3? Oh, this is condition.
All the conditions, those are the initial condition and the boundary condition.
So we have nth order, so we only need to pose
the equation is nth order. So you only
need n conditions anyway.
N plus 1. It's an initial condition plus n boundary condition. But
that still will be overdetermined. We just only need n conditions. We don't need n plus 1. If n plus 1,
I mean, let's move to the examples because in
Okay,
general,
okay. N
it's
plus 1
more
is right. N plus 1.
complicated.
N plus 1 is right. Okay.
Yeah. Let me think which example go first. Okay, let's do the following.
If you find that interval x goes from 0 to L, how many boundary conditions we need? You say
Still, for
1
this case,
plus 2 or n or
1 plus n, one initial data and n boundary value, because you have two
so we
boundaries.
can choose from 2 and 3, just n, right?
Yes, totally n. But at least one from each. At least one.
Up to the n.
Yes. So you can choose n from 2 and little n minus capital N from 3 for the interval or half line. Okay, let's say example. So first example is the simplest one. So we will consider the shading equation. And we will consider shading equation on the whole real line. So for this one, you only need the initial data. And let's say, so this example is to for the purpose of a review inverse scattering. So we will solve this equation by the method of inverse scattering. So the first step,
So
you find the last
we don't need a boundary condition, right, for this one?
Yes, we don't need, because we are talking the whole real line. If it's a half line, then we can post a boundary condition. But for the, actually we have the boundary condition. So here it's because we post a decay behavior at the infinity. So that means, so for any t, you actually post some boundary condition at those infinity. But if it is a finite line or a half line, then you can post a boundary condition on this boundary. But in this case, we don't have boundary, so it's just assume the initial data is decaying at infinity. So it's already well posed. And let's solve this equation by inverse scattering. So Lux pair. For this equation, it's very easy to find the Lux pair because it's a linear evolutionary constant coefficient PDE. So we can find the Lux pair mu x minus ik. So k is a spectral variable. Q is a potential to the equation, and mu t is very easy. You can find this. IQX minus KQ. So any question about the Lux pair? Or do I need to deliver the Lux pair for you? There's a general way to find the Lux pair for the linear.
I think this is the Lux pair posted by Fokas in 1997 in his first paper to raise the unified method, 1997 in JPA. So I just checked the history anyway. And here, this Lux pair is not the real Lux pair. This kind of, because this Lux pair is non-homogeneous. If Q is not there, it's not homogeneous. But anyway, the countability still give us the heating.
Yes. So,
and this is his creative work. He all work based on this. All later work based on this.
But here, this Lux pair, it's like a concept to find the exact form, actually. So from this Lux pair, we can find we can solve the ODE now. So mu, so from the first equation, we can actually solve it. And also we can define by the analyticity equal to e to the I k x minus c q c d c. For image k in the upper half plane or lower half plane. So mu plus means it's analytic on the upper half plane, and mu minus is analytic on the lower half plane. It's very simple. The equation, the first equation, you can solve it. And also we already post the boundary condition here, right? And mu limit x go to so e to the minus kx, x go to, what is this? So it will go to e to the minus I k c q c. So this is exactly the Fourier transform, basically. Fourier transform the initial data. So, okay, let's put the 0 here. It's true for any t basic, but so let's denote this by alpha k. Now you will see plus minus is analytic in up half plane. So we can actually construct a riemann-hilbert problem. So the second step, Riemann-Hilbert problem. So we want to see it's directly from the equation. So you just subtract mu plus by mu minus. You will easily see this is just the minus infinity to infinity into the minus I k c. Let me see. No. I k x minus c q c. So this is what? E to the I k x alpha k. So from this RHP, we can easily solve the equation. And by the primary formula, we have mu z equal to the, okay, let's use this one. So mu z is Cauchy transform of this density. So it's 2 pi I e to the I s x alpha s minus k ds. So k is a complex number. So here I have I actually implicitly post a condition that mu is this. So our RHP is normalized by this condition. So you have RHP. So basically now you have done the direct scattering, and how to do the inverse scattering. So you need to connect the RHP, the solution to the RHP and the potential. So let's from step 3. Recover potential. And again, from the spectral problem, and you let mu be this, okay, plus O. And you plug into star, you will say Q X, let's say Q is minus I mu1 X. And what is mu1? Mu1 you can derive from the solution to the RHP. So mu1 is, no. So since mu z is 2 pi I, this e to the I s x alpha s. So you can s minus k ds. So you times k, and let k go to infinity. So k go to infinity. This give you minus 2 pi I e to the I s x alpha s ds. Ds, yeah. So
Hold on.
yes.
For the expression of u, why did you didn't start at what, at the first order for the rest and you went to 1 over k? Is there a reason why you did this one here?
Because my initial data is in Schwarz space, so it's vanished at infinity. So there's no constant term.
That's what you start at what, at the second order.
What do you mean?
I'm talking about the u, the expression of u.
Oh, the star equation.
So start a question, what's wrong?
I said, why did you start?
What kind of asymptotic here for mu at x infinity, at k infinity?
Yes.
Yes.
Why you have such kind of asymptotic assumption, some property of? In the
This one is just from, okay, this is from the integral by parts. So for this one, you integral by parts, you just got this decay. It's very simple. If the initial data is in L1, that's sufficient to guarantee this kind of asymptotic. But we are living in Schwarz data, so even better. Okay.
Okay.
It's just you can apply the Riemann-hilbert lemma. Or integral by parts if you are in Schwarz space. So combine these two, what do we got? We have Q equal to 2 pi e to the I s x alpha s ds. And what is this? This is exactly the Fourier inverse. So that's totally equivalent to the classic method. You do the inverse, you do the Fourier transform and you do the Fourier inverse transform.
Could you write down the Q more clearly? In plug the alpha. Plug alpha. What is alpha? Yes. Then you just work out by using initial data to present the Q. So alpha is inverse, right? The Fourier transformation of initial data. So this is a Q0. You just use Q, right? So this is a, is this the same as the heat kernel? Because the Cauchy problem, this is a heat equation, right?
No, this is a wave equation.
Sure.
That's a Schrödinger equation.
Yeah, Schrödinger equation. So
this is
Schrödinger
wave
equation.
equation.
Yeah, this is actually, yeah. If you just if you just use a new variable it as a t, so this is just heat equation. Or
of course, but
so heat equation we can present by using heat kernel, but this is not a heat kernel, very different.
no. This equation is very simple. I just want to like review the inverse scattering, because.
But anyway, the result should be the same, right? heat equation, the Cauchy property heat equation presented by heat kernel. Heat kernel, you have the integration with the arrow function anyway.
No, it's not done yet. I have a step 4. You need a time evolution because here we didn't use the
Oh,
second.
don't involve time t. Okay, okay.
Yeah.
Right.
That's where the heat kernel will come.
Yeah, you're right.
So time evolution. Because this method is very general. It's not just for the linear equation. You can generalize this procedure to the nonlinear equation. But that's the idea of the inverse scattering. So time evolution comes from where? It's from the from this asymptotic behavior. So, and from the second equation, we have
the step 3 actually did nothing about beyond besides the Fourier transform, right?
It's exactly Fourier transform.
The Fourier transform and inverse Fourier transform. Okay.
Yes, so it just cancel out. I mean, this problem is very trivial, so you can use classic method like Fourier transform to solve it. But here I just want to present in the inverse scattering manner.
Right.
So so we have like this thing. So plug into the second equation, you have, and the right-hand side is the IQX minus KQ. And this thing will go to 0 as X go to infinity. And this will go to alpha. This will go to alpha. And you solve this ODE. So basically, if you do the Fourier transform, this is the ODE you get when you do the Fourier transform to the first equation. And what you got? So alpha is alpha kt, let's say, equal to e to the minus I k squared t alpha k, t equal to 0. Then you just plug into the this equation. So step 5, you got solution equal to e to the isx minus ik squared t alpha k. So the variable is s. So alpha s ds. So this is the solution to the Schrodinger equation, the linear Schrodinger equation. And that's the whole procedure for the inverse scattering. For general nonlinear PDE, integral PDE, and do the same thing.
Do you have confusion about the notation? Previously, you use alpha to present the Laplace transform of the Cauchy data. Here,
Yes.
Here alpha is asymptotic condition.
No, same alpha.
Same alpha.
So the asymptotic is here. It's here. So this alpha is exactly the Fourier transform of the initial data.
Oh.
That's the beauty of the method, because inverse scattering is a generalized Fourier transform.
Simple case, right? Okay.
Yeah, because it's the equation is simple, so there's a lot of simplification. So, any question about the example 1? We can move to next equation. So, as I mentioned, this procedure can apply to nonlinear PDE as long as you have the Lax pair. Okay, let's move to example 2. So this time we are talking, we will consider the heat equation. And we will discuss the equation on the half line. Still, this equation is very simple. You can solve by classical method, so-called method of image. So we are considered on x on the positive real line, and t part doesn't matter. This capital T can be infinity. So we need the initial data for x plus, and one boundary condition q 0t equal to g0t for t in the. So what does the problem looks like in the phase space? T x. So let's say here is capital T. So we want to find the solution in this strip. And the initial data is given here. We have a Q0. And we have, sorry.
Not a large half.
Yeah, just half, sorry. No such thing here. So, and here we have the boundary data, G naught T. For this one, we want to determine this blue region. And let's say how we solve it.
You should use A or use GH. One is Q, one is G. Okay, good.
Yeah. GH.
These are two functions.
Example 2. So, and we're not going to use the classical method, but since we're talking Fokas method, so that's how Fokas method work. The first step 1, actually, basically, you still need to find the Lax pair, but since this is a linear equation, it's very simple. The idea is to find the one form, exact one form. So for this case, it's very easy to find the one form. Let's denote by W. So it's e to the theta x tk q dx plus qx plus ikq dt. So this one form is exact. This theta is basically the dispersion relation. If let me write down ikx plus k squared t. It's just directly from the equation, and you will see this is actually d.
In the equation, hold on. In the equation, do you need I?
No, heat equation. Now we are talking heat equation.
Then your theta, you have the complex I there. So do you think the theta should be complex or just real?
Complex. It is this. It is this way. No problem. Because
this theta, this is not this. Do you think this is the phase shift of the theta equation?
Yeah. Because in classic method, you do the Fourier. It's a Fourier mode. Kx and ckT. You do the expansion of this. Okay. Take all the integers. So you plug in 2 and you can determine all those things. That's a classical way.
Then your dispersion relation is complex because the heat equation dispersion relation is real. From theta, the dispersion relation is complex. That's why I want.
No, heat equation doesn't have dispersion relation, but
heat equation you do have the dispersion relation, right? Why you don't have all?
It's a heat equation.
You have complex. Okay, you have complex. So that's why you have okay, that match. Then match. Okay.
I mean, it doesn't really matter, but
then the decay you have problem, right?
There's no decay.
Theta, if you do integral, definitely you need a decay condition.
Yes, of
So
course. I mean,
decay-
from physics, of course, the initial data will decay.
Decay, so that's why T is bounded region. So you cannot take
Yeah, yeah.
T
Fixed T,
infinity.
for fixed T, it
Right.
will decay at infinity when x go to infinity. So,
E theta already goes infinity. So if your T goes infinity, so T must be bounded.
T is fixed, yes.
Okay.
T is fixed, and so the x part is oscillating. That's the heat current, basically. And you will see this is exact, but actually it's connect to the Lax pair, but it's not important for the purpose. And this omega is exact, and it is so d omega is 0, of course. So we can use the Green theorem. How does this work? So let's consider here R of this contour. So we integral. Let's say this region is D of this one form is 0, right? Because it's exact, so the any loop is give you a 0 integral, any path integral, and this will give you, so you let this R go to infinity.
Could you show your original problem? Do you bound it? So you half line, right? Or
Yes.
anyway, you just take the finite D and then let R
T
go.
is fixed. Yeah, finite time.
I want to say what is a capital T? Is capital T is finite or can be infinity?
It's anything, but you have to fix it. So when you describe this phenomena, you have to fix T. So the thing is, we are looking for this thing is decaying for x go to infinity for fixed T. So if T is fixed, then this thing will decay when x go to infinity.
Right.
That's kind of this solution we are looking for. So and is
We have to talk about domain for x and t. So what is the domain x and t? X is half line, t is finite interval from 0 to capital T. Cannot
yes.
go to infinity. If you get to infinity, right, the integration may cause problem, right? Because the decay may cause problem, may not decay. I mean, the whole integral from 0 to infinity for t doesn't exist.
Yes, but
Anyway, so that's why they use capital T anyway.
no, but this capital T can be anything actually.
Capital T, if capital T equal to infinity, the problem is very different.
When you get a solution, you can actually let capital T go to infinity. Because we will say,
you don't do integration from, I mean, 0 to capital T, right? If you do integration from 0 to capital T, then you have problem.
the integration is from 0 to
So 0 plus then T go to infinity, so you have integration from for the whole half line for T, then you have guaranteed the decay.
Yeah, this decay will guarantee on this thing. So it's based on the
Go ahead and we will see. Let's see.
Yeah. So
the procedure will work.
Use the Green theorem. You will see. So this is the first integral is this line, so it's 0 to infinity, and e to the theta. So we have this one form, and in this line integral, it is x is x is here, and t is 0, and q x0 dx. and minus this one. So let's say this is 1, this is 2, this is 3. So here is from 1 and 2 give you this integral from 0 to t. So here is capital T, e to the theta 0 tau k and q x 0 tau plus I k q 0 tau d tau. And this equal to 3, which is from 0 to infinity. So because I moved to the right hand side, I changed the direction. So it's from 0 to infinity, e to the theta x t k q x t dx. And this thing is very important in the, is the basically the whole idea of the Fokas method. It's called the, so this is called global relation. And in this trivial example, we will see it basically gave you the solution. So let me just introduce some notation. Q hat, Q naught hat is this e to the minus I k x q x naught dx. So this is basically the first integral, because this theta when t equals 0, it's exactly minus I kx. And g naught tilde omega k t equal to 0 to t e to the omega tau q 0 tau d tau, and g1 omega k tau e to the omega tau qx 0 tau. So here one need to be careful because our initial data doesn't include the first derivative. So this data is unknown. And okay. So this global relation will become Q naught K minus G1 tilde omega T plus IK G0 tilde omega T equal to e to the K squared T Q hat KT. I just rewrite the global relation. Then you replace T by little t, and you do the Fourier inverse. You actually got qxt equal to e to the ikx minus omega t q naught at k dk minus 2 pi e to the ikx minus omega t, this thing. So let's copy this. G1 omega t plus ik g naught omega t dk. So for now, you already have a representation of the solution, but unfortunately, it's not, we still have something unknown. So because G tilde is from the data for Qx, but we don't know Qx. So we need to remove this thing. Otherwise, it's not a solution at all, right? So how to remove this thing? This is a very clever way. So for the global relation, you need to find the discrete symmetry of this relation. So you change k to the minus k. You will say q naught minus k minus g1 omega t. So omega doesn't change because it's k square. Yes. And minus ik g naught omega t equal to e to the k squared t q minus t. So by this relation, you can replace G1 by the data of this and this and this. So our solution will become 2 pi e to the I kx minus omega t q naught k dk minus e to the, any questions? Q naught minus k plus 2ik q g naught tilde omega t dk. And plus something else, q hat minus k t dk. So here, those things are we all know the data is from the initial data. So this is from initial data, and this is from the boundary data, boundary values. So we need to analyze this thing, and we will say this thing is actually equal to 0. So this thing is, so we will see why this,
Fudun.
yes.
So this clever trick you said, so it should work if the dispersion relation, the omega is invariant, doesn't change, right?
Yes, so basically you need to find so omega k equal to omega vk. So this v transform a k to another thing. So if you have a n relation, then you can reduce the equation. You can reduce those unknown boundary conditions.
Without this condition, we cannot do it in general.
But fortunately, if omega is a polynomial, you can always find if the degree is n, you can find n minus 1 symmetry. In a typical example, it always be a polynomial. So you don't need to worry about the symmetry. You can always find those. So let's say why the last integral is 0. Okay. So what is q hat minus kt? Let me think. So this thing is the Fourier transform of so you change the k to the minus k, so it's I x q x t dx from 0 to infinity. And since our q is bounded, so it will be, any questions? Analytic in upper plane. So we can deform the contour. This is 0. We can deform this contour to here. And this gives us e to the I kx q hat minus kt dk equal to, so let's denote this area d. So it's the boundary of d, e to the I kx q hat minus kt dk. And let's say dkr. So and you will say it will decay on this this arc. So you let r go to infinity, it will go to here is the Kirsch theorem. It will transport to the arc. So sorry, the integral on this contour will transport to the integral of this contour. So the first one is here, so this will deform to this one, and this contour will deform to this arc because it's analytic on the up half plane. So this eventually will become, let's say this is CR, and R go to infinity, e to the I kx q minus kt dk, and this is 0. So to summarize, we got the solution qxt equal to this whole. Sorry.
The symbol pretty confused actually. In yeah, kxt, yeah, kxt earlier formula is not very clear.
No, q.
Earlier, the formula earlier before this, your picture. Yeah. Just pass it. Just pass it. Yeah, later. Yeah. The last line. Last line. Yeah. What is the x in the left hand side? Oh, no x, because integrated with x. You have just k and t. So what is the t is a parameter, right? T is just parameter. So you are doing the inverse scaling.
Inverse inversion. Fourier transform.
X.
Inverse transform.
Okay, for x. So t is fixed.
T doesn't matter actually in this case.
T is fixed. Okay, go ahead. Let me show. Could you show the later something? Okay.
So I just proved
why,
that.
Why then you need the negative k? Because what? If the k doesn't go 0, or
No. Because we use symmetry with the global relation. So we want to replace this G1 by other data we know.
Yeah, right. But if you use a G hat k t, that term still goes 0, also goes 0, right? So if you use q hat kt, that term still goes 0.
Which term? This term?
Yeah, when.
No, it's not. You have something else. It will go to something like this. It's different.
Why don't it go 0? Because you don't need any.
Also, we don't know what is this thing because we don't know the data about GX.
Right, I mean, talking about take the negative k. Take a negative k and take the k which is the same.
It's different.
Why different?
Because here,
where
the relation is totally different. This is the original global relation, There's ik, and if we change the k to the minus k, because the x part is linear dependent in k, but the t part is k squared. So there's some symmetry about the global relation, but this global relation is for all k, so this doesn't matter.
Then what? For the original one, you still will be able to solve for G0 theta. So no problem.
Or
You still can solve for that, then replace that into.
no. If you replace this thing, you got just the backwards, I think.
Nothing we get it. I mean. Problem with nothing get it. That's why you needed the
Yeah.
problem. But if you don't have the symmetry property, then what you can do? For general,
Will have. I mean, if you don't have symmetry, then the problem may be opposed. Because for
cannot solve by this procedure.
yeah, maybe. So maybe you need some new ideas. But yeah, to pick an example for evolution equation, you definitely got some.
For evolution,
polynomial.
for the starting equation you studied today, that general evolution equation, then you don't have the such kind of even
No,
property.
you have. For any polynomial, you can find for a polynomial of a degree n, you have n minus 1 symmetry. You can always find those.
Do you think so?
It's just a finite group, so it's I mean, you may not able to write down the formula explicitly, but
is the general polynomial. General polynomial is not even.
I mean, existence no problem, but write down the transformation is hard. But usually for low order, we can write down the transformation explicitly.
For order, you can determine some kind of transformation. But
yeah, the group, it's a finite group, so you can always determine this.
Some kind of symmetry.
So, okay, are we good for this example? Next example will be the nonlinear Schrödinger equation. And I think we don't have time for today.
Only 1 hour.
Let's discuss something maybe.
I think you are explaining. Yes, which is good. Anyway, I should say I'm fine. Could you finish it maybe in 15 minutes or 20 minutes for the nonlinear Schrödinger?
Yeah, at least to present the general idea, maybe.
Sure.
I mean,
so,
the example very clear. I think Fu don't really just explain everything. All 4 steps very clear by these 2 examples.
But this linear case is very useful.
Really, Fu don't really explore it for us actually, which is really good. Yeah, I'm reading so many papers actually in seeking in some kind of complex analysis management. I think the author didn't tell you, which is really, I mean, essential part or essential, the key you have to go through it. I understand pretty much clear today actually, Fokas method anyway. Fokas method actually assume you have the well-posed problem, then you can present a solution by using your boundary value and initial value. And he just tried to explore some kind of relation about this, about the presentation of the solution. Anyway,
the Fokas method has a lot of advantages. For example, if you want to solve the linear KdV, classic method doesn't work or doesn't give you good results, but the Fokas method gives you a very good representation. But that's something else. We are not
for linear KdV Cauchy problem, definitely we can just use the Fourier transform. We can
yes, but for initial boundary value problem, like on the half line.
We're talk about much anyway. The boundary value just
then it's a, I mean, classic method you can solve.
Boundary value problem, particularly on the finite interval. Yeah, it's really hard. Actually,
yeah. The most difficult cases.
Undergraduate textbook, the PD, chapter 4, the wave equation section, chapter 4. Peter explore actually different kind of boundary value problem for the wave equation.
Classic method is use separation variable, but doesn't work for general equation. Okay, let me mention something about nonlinear shading equation then. So
yeah, we can stop at maybe, yeah, I mean 10,
yes,
30, I mean 10, 30.
I can skip the
We
idea.
may use 10 or 15 minutes, maybe tell us the example.
So nonlinear shading equation on interval. So which is harder? Because on the real line is the simplest, and on the half line is a little bit harder, and on the interval is the hardest. And the equation, let me write down, IQT QXX minus Q, and we are talking the defoxing on T is still bounded by capital T. So QX0 is Q naught, and we need 2 boundary condition at least. Q G0T and Q on L is F0T. So what does the problem looks like on the phase space? So T and X. Here you have L and capital T. And let's denote those points by 1, 2, 3, 4. Again, the first step is Lax pair. And this is it's well known for the nonlinear shading equation. We can write down the Lax pair, but now it's a matrix form. You can derive this from AKN hierarchy or Zaharov-Schabert's system. And we write this in Beers-Kaufmann's form. Q mu t plus ik square, 2ik square, sigma 3 adjunct, mu q tilde. And the q tilde you can determine it's a second order, it's a linear polynomial in K. And again, you need to find the exact one form. So from the Lax pair, you can easily find the exact one form. So W x t k is e to the I theta q mu dx plus q tilde mu dt. Then for a point x in this region, we can solve the spectral problem simultaneously. So by this exact one form. So, and it's a line integral and it doesn't depend on paths. So mu x t k equal to, here we normalize the eigenfunction, this spectral function at this corner be the identity. So we have t x t e to the minus I theta x t k sigma 3 w y tau k. So w is a one form, and this is a line integral. Then by the different normalization, mu j at point j, pj is I. Then you can determine for spectral problem mu1, mu2, mu3, and mu4, and they are connected. They are not exactly connected, but they are connected because the the OD is first order system. So we can we can define the so-called scattering matrix. So mu3 is mu2 e to the minus I theta. Okay, mu1 is mu2 e to the minus I theta sigma 3 sk, and mu4 is mu3 e to the minus I theta minus lk slk. And it's very easy to determine those sk, capital sk and slk. And the next step is very essential. You will see. So in the first quadrant, you will see mu2, the first column, and the second column, mu4, are analytic in this region. And
Could you
yeah.
explain why they choose this as small s, capital S?
So this choice is arbitrary because every two matrix is connected. But why choose this one? For the first two equations, it's very. I think the motivation is because mu2 is normalized at this corner. So this corner is means mu2 0 0 k is identity. So that means sk is just the mu3 0 0 k. Capital SK is mu1 0 0 k. And for the last relation, I don't have any motivation, but it just arbitrary.
So this will be this will be actually also just
It's just your choice.
Some mu3 problem at L, not at 0, 0 L, L 0 problem.
Mu3 is this. Mu3 is L0K equal to identity. But it doesn't really matter because it's just a different path to compute things. But after all, it's equivalent. So the important thing is from this integral equation. So this is an integral equation about the mu. Yes. You can find the analyticity of the columns, which is we do for usually inverse scattering. And like for this case, you will see there's a jump on this contour because there's two analytic matrix, and you can find the jump J1, and you can formulate a riemann-hilbert problem.
How can you exploit U1, U21, and U42 analytically in first quadrant? From where? From original integral equation, right?
Yeah.
So you have analyzed original integration very carefully, I mean, right?
Yes.
So determining which column of the eigen function mu j is analytical, where sort of things, where and which.
Actually, I have a table, but I don't want to write. So each different column in which quadrant it's analytic, you can analysis this. Okay. Actually, it's very easy to see from the equation.
From Water integral equation.
Yes. As long as the exponential is decay, then it is analytic.
Okay. What is the other part two? The third quadrant and fourth.
So it's mu4, the first column, mu2, and mu3, mu1, 2. And I think it's very, you can generalize to even multiple components.
And compute out to the jump matrix, not that easy, huh?
It's very easy.
Let's say how to compute J1.
I didn't compute J1, but I computed J2.
Yeah, tell us how about compute J2. Yes.
So, so you will see what is J2. So you need connect. So we oriented it like this. So this is the left and this right. So mu4 equal to and J2, right? So this is a Riemann-Hilbert problem. We want to determine J2. And what we have is those relation here.
SLK is mu4 L0K. L0K. SLK last jump metric SLK or the scaling transform metric SLK is just mu4 L0K. They really work out very simply. So yeah. Anyway.
Yes.
You are working. Okay, you are working out. Okay, J2. Okay. Or how?
So
how can you find this equation? Yeah.
So from those three equations, you can find mu4 equal to mu2 e to the minus I theta sigma 3. Beta is e to the I LK sigma 3 is LK. Then you just figure out what is J2. That's it. Those two systems are equivalent. Just change the order of the matrix. There's some details.
Some detail anyway. Good. Yeah.
But the idea is just exactly what we did before for inverse scattering. There's no difference.
Okay. I don't want to use more time. You go ahead.
And the last part is to derive the global relation. And this is the whole idea of the Fokas method. And this thing is from the just compute mu4 0tk. And you compute this thing, it will give you a global relation. And I can talk details next time, maybe. The next part, the rest of work is just analysis the RHP and analysis the spectral problem. Those are just a very standard technique.
Okay, good.
So far you're still on the that first paper, right?
No, there's at least 3 papers.
No. I just mean what you covered today. I mean,
Yes, I covered 3 papers.
Okay, this is just all right.
So different example from different paper.
Well, sure, yeah, okay.
I think Fox has a bunch of papers about the integration presentation of the Cauchy and boundary value problem for linear and nonlinear PDEs. And
Yeah,
you may look at it. We are talking about nonlinear shooting, so you just look at the 3 papers. Nonlinear shooting on half-line, nonlinear boundary value problem.
And not half-line, half-line is too
finite interval, and then actually they have new paper on the circle, the periodical situation. So you can just check the 2 papers. Yeah. Check on the half-line, on the finite interval, 2 papers previously. And
I'm just wondering if the overview is more or less the same, Fudong. In the recent, yeah.
Actually, Fudong maybe jointly read some other papers. Fox has many papers on linear partial different equation and non-linear. Schrödinger is non-linear. So only from the Schrödinger, he published 3 papers.
To get the idea, it's just
okay. Fudong. So
Fudong tell us which paper. Yeah, I mean we should read first or focus on.
Yes, but the overview, in the most recent paper is adequate. No, I mean
recent paper is hard, I should say, but tell us.
Well, yeah, but it makes the connections
read about to get the basic idea. Yeah.
Okay.
Yeah, but it makes the connections much more clear without getting bogged down by the details. So just wondering if it's comfortable.
I mean, if you can do the interval case, you can do anything. So my suggestion is to read the Fokas 2005 paper.
Okay.
I suggest Brittany, I suggest you read the Fokas paper with it on the finite interval, because we'll talk about that's pretty hard. But anyway, before that paper,
yeah, I'm pretty sure the new paper includes that.
yeah, 4 paper includes that.
So,
and but a 4 paper that includes the non-Newtonian equation on half-line. You should read that paper as well. Otherwise,
half-line is very
yeah,
hard.
I have them here. It's just that you know, I found that this
will be sufficient for you to understand the basic idea and the solution procedure.
Yeah, I tend to work from the top.
Yeah.
I tend to work from the top down, like the general idea first, and then go into the details, or else I don't.
General idea, I think don't really give us, because if you have no idea about Fokas methods, definitely today's talk is talk is a little bit difficult for you. But if you read it, gradually you will see the solution procedure very clear. It's not something really difficult, but yeah, it's some kind of the problem is how to present a solution to Cauchy and a boundary value problem for the PDE. So you need the Cauchy data, you need initial condition and boundary condition to present a solution. And how many this kind of condition will be sufficient to present a solution, and nobody can tell. But here, in the Fokas method, through the analysis of the global relation, you will see what sufficient conditions, what is number sufficient condition you need to present the solution in integral by using integral presentations, through the integrals, this kind of idea. Yeah. So this is a little bit more general than Fourier transformation. Fourier transformation only just solve the Cauchy problem. Boundary problem, I think, very hard use the Fourier transformation. But anyway, here Fokas method can solve both. So Cauchy problem and solve boundary value problem. This is what I understand. Yeah, this is just my understanding.
So you can read this Cambridge lecture.
Oh yeah, the textbook. I downloaded the textbook. If you read it, probably. Yeah. How can
textbook
I?
Is
let me see the. Yeah.
This is a lecture in Cambridge.
Yeah. Okay. Yeah. Publish a unified approach to boundary value problem. I think this paper pretty simple, easy to read, but you need time. You need, if you want to understand, this is a book about maybe how many, 600 pages? How many pages?
300.
Yeah, huh? 300.
The book is too much.
Much. What is this? This is just paper?
It's I think it's Fokas lecture.
Fokas lecture. Okay. This is just a lecture. Yeah, it's good. Foden gives us a lecture. I think this is good. Yeah, this is good to read.
That's 30 pages.
Yeah, this is pretty good, I think. Yeah, that's better. But if you can,
great. Yeah,
if you can read the textbook as well. Textbook is where is the? You can read a textbook called A Unified. Could you, Foden, can you give us a link about textbook?
Or you could just type the title and
I type the title. I'm typing the title.
Yeah, so yeah, and maybe one of the authors or whatever.
Value problem. I'm typing, so you don't need to type. Unified. By Willie, I think.
SIM, I think.
Huh?
It's SIM.
Or SIM. Or by SIM, 2008. Okay, so you can search this. You can download this book. SIM. I'm sorry, M is capital. So this is pretty. I think a pretty easy book to read, but you need the time anyway. Yeah, Fokas really. Yeah.
Okay, thank you.
But generally speaking, I should say, Fokas method doesn't guarantee existence. So I have good idea for you. I have got a question for you. We have the presentation of the solution, right? So we can use this presentation of the solution to prove the existence, right?
No.
Why?
No, I mean for non-linear equation, it's hard. For linear,
you just say this is the solution to our boundary value problem. So the existence can be guaranteed once the boundary value, initial value given.
No, it's a very hardcore analysis because
Or very hard to differentiate it, right?
no, their proof is based on the existence of the
Right. Basically, you can prove it, but then once you present the solution by using Cauchy data and boundary data, then you can present that is just give us a solution to our Cauchy and boundary value problem.
No, this method is exactly like inverse scattering. You cannot prove existence because you have to assume the existence of the Riemann-hilbert problem. And in this case, you have to assume the existence of the global relation. So you have to
But anyway, I mean, because you got a solution already by using Cauchy data and boundary data.
Yes.
So then you just that function, you prove this function just satisfy our our problem. Then you prove the existence because we just use the.
In this representation, you use the global relation, and you have to solve the global relation.
Oh, global relation
The
exists.
global relation is nonlinear. The global relation is nonlinear. So
and doesn't guarantee because we just assume you have the solution there. Okay, for that we don't solve it. You have to prove the existence for the global relation.
So I think for different equation, people will do another paper like do the well-postedness or existence. Like
yeah, that's very hard, really very hard.
I remember they mentioned this issue of well-posedness in the recent paper, but I don't remember precise
many
details.
people for the nonlinear PDE, the existence theory is very difficult. Very difficult.
I mean, that's for PDE people.
PDE people will love to. I learned something about subwoofer and estimation sort of things, but I never did any example. I want to do some example anyway. Probably for some easy linear equation, we can really do that. For high order, for example, fifth order linear KDV, probably we can do that. We can explore existence. So the initial and boundary value problem. That should be very good work. Yeah. Could be written into some textbook. Good. Any question for today? Anyway, yeah. So.
They mentioned actually that this the Fokas method, I guess. They say this method has led to a new rigorous treatment of the question of well-posedness for nonlinear evolution PDEs, and they list 2 papers.
Yeah. This method is pretty new, so there's a lot of mathematical thing you need to solve.
Right.
But it's very popular in the numeric analysis of the nonlinear PDE.
Then you can just compute the numeric solution by this kind of procedure. But anyway,
it's very effective because
existence. I think one is you have to guarantee the solution exists.
Why is it? Sorry, why is it effective in numerical calculations?
Because you have an integral representation, and this representation gives you uniformly convergence. Not the classic method give you like a Fourier transform representation. It's not uniformly convergent. So different.
And yes, but so why is that helpful for computations? Meaning numerical computations, and why is that specifically useful?
Because you have a representation, you can do the computation.
Okay.
I think yeah, but it's still pretty complicated. I think global relation is bring us a new problem.
Udon, I have a question.
Yeah, please.
So I just want to ask. Okay, what is it? Yeah. So about the analyticity, you get the U1, U3, U4 from the fundamental solution, right?
What do you mean fundamental solution?
So you consider the right hand side of R equation to be 0, and you just solve them.
No, it's
like the matrix, our matrix equations.
I mean, the Yes, the potential is decay at infinity.
Yeah,
It
and
usually be assumed,
and you
but
solve the fundamental solution, you got our U1, U3, U4.
you don't need to solve those things.
No, I mean, you solved our lax equations, and that's how you get. That's how you get this.
Yeah, from the, I mean, this Lux equation is just a simple ODE. You can
Exactly.
directly
So
write
you
down.
consider the U and U delta to be 0, and you get them. You get our equations.
No, I mean, giving this form, I can directly write down the solution, general solution.
Yes, exactly. Yes, this is what I mean. Yes.
Mhm.
Okay. Okay. My other question. So you did the focus method now for our NLS equation, right?
Yes.
So can you do it for a coupled NLS equations?
Or that
I think people already did. I think
very few work, I think, not many.
Because in that case you're gonna have integral of exponential, and our exponential will be a matrix, and you don't have commutativity in that case.
Yeah, much hard, but some work.
So yeah, it will be much harder, but I think it's doable.
no, the only effect, only thing will affect is symmetry of this S. So in our case, you do the reduction. So this SK will looks like AK or BK bar.
It also affects the equation, the integral equation, like the one that equivalent to our Volterra integral equation. It affects it because
the inverse scattering still works. You can use.
it still works, but you will have like.
I think it will be more simple because you have more freedom. Because you can use left scattering, right scattering. There's no, it's not coupled. It's not coupled. For the scattering, it's not coupled. I mean, for the equation, it is coupled.
For the coupled case, the problem will become much more complicated.
Yes, it will be much more complicated. It will not be.
First,
I mean, the general idea will work, but it will be much more.
First, Riemann-Hilbert problem may not be solvable.
I think it depends. It depends on the
problem. We don't know what.
It depends on. No, the Riemann-Hilbert problem will be solvable, but it depends on our
in general not solvable.
No, it will be solvable. It depends on our Lax pair. It will depends on our first member of the Lax pair, the U.
Lax pair is the high order solvability because you have variable coefficient. Solvability still has a problem. So how can you present mu? And this is the first problem. Okay, we don't just argue because the high order system, the solution is still not easy to present. Then second problem is how can you choose boundary value? As Fudong actually mentioned, you have many choice for the boundary. If you have U1, U2 on the boundary from x equal to L, then what kind of boundary you should choose? You choose U1 just first order and U2 second order, or what kind of boundary value you should choose with respect to x? I mean, which order derivative you should fix? Nobody knows. So much more hard. So for the coupled case, I think Fokas really for all Fokas work focus on single equation so far. I think
for coupled it will work.
For coupled equation much hard. How
much
can
hard,
you
but it
the
will
boundary
work.
value problem? Yeah.
Yes, but it will work. I'm sure it will work.
If you you can work out some problem. I think for sure. Yeah. But generally boundary value problem it's really hard actually.
The problem is very hard. Even for linear PDE, it's still
even linear very hard. Yeah, you're right.
It's
even
a very new
hard.
method.
Yeah, the analysis is just almost unreadable. If you look at it, I'm reading his general paper about the general evolution equations. Wow, that's just even unreadable. His analysis they are just too complicated. But anyway, Fudong gave us very clear idea of sort of this 32 example actually.
Yes, very clear talk. Yes.
Yeah, I recorded it, so I will publish the recording on the Google Drive, so you can download to it. So it's very clear.
Fudong, also can you scan the analyticity of the U1s in the upper and lower and send it?
Presentation, you can send us a PDF file as well.
or like a PDF file?
No, it's on the paper. I mean,
Oh,
it's useless to just read my notes because you have to write down the equation and check it once
okay.
by yourself.
Yeah, I know. Just I need it direct. So.
It's not difficult. I mean,
But in the
Yes,
recording,
yes.
in the recording, Ahmed, in recording you can read it because in recording you can just move around to see the writing.
I mean, I will if next time I can present the details different.
You next time what you present? Tell us. Present the nonlinear shooting equation on finite interval. Or
Yes, because I didn't finish the circle.
right. So let's focus on the finite nonlinear shooting on finite interval. That paper actually by
Fokas, yes,
Fokas and Eads, published in JPA 2004. I guess, right?
Paper is very short and simple.
Paper is very. It's not short. I
It's
don't.
like 20 pages. Very short.
Or 20 pages. Or 20 pages long.
30 pages.
Or 30 pages long. Yeah. Yeah, publish it. Yeah, on JPA 2004. The nonlinear shooting equation on the interval.
Oh, I'm reading the archive version.
Yeah, this is the published version. It's better actually. They remove some errors actually.
I don't know. Maybe they update some version.
Good. Any more questions from young people? Next time I think Fulton will talk about nonlinear shooting equation on the final interval.
So this will be in 2 weeks.
In 2 weeks, yeah. I think 22 April, right? 22 April, Thursday. So we have spring break next week. So you can go somewhere, have some vacation, take a break, and prepare the next.
I don't think so, but
and we have just 2 weeks left. And folks, believe me, Fokas
Yes.
method is pretty hard. I think you just get an idea. Okay, we do have such kind of powerful method to solve the boundary value problem, Cauchy and boundary value problem.
yeah, I mean,
Linear and nonlinear PD, which is really rare, of course.
I
But
skimmed
there's a lot of problem there, right? As we discussed, as we realize now, the
Mhm.
existence cannot be guaranteed.
Okay.
So still a lot of problem. Yeah,
Yeah, I skimmed through the more recent paper, and it's really nice. It really like
they publish many. They publish, I think,
it makes the connections very
papers
clear for me.
at least hundreds papers about Fokas method now. Yeah, so,
Yeah, well,
but focus on the basic
That's
one.
a good method.
Now shooting a modified KDV. This is nonlinear and sine Gordon. This is basic equation. It's good, sufficient to learn.
It could be a dissertation. It's a very good method.
Oh, you like it very much because it uses a lot of complexity. Actually, some people also give some negative comments. They say because you cannot guarantee the existence.
Yeah.
Which
That's why.
you just transform one presentation to another presentation of the solution. So do a lot of analysis, which is not useful. Some people say that, but anyway.
That's why you still can publish paper on this field. Otherwise, no fundamental job you
different
can do.
things are
You're
quote
right.
unquote important to different people, I guess.
Yes. Anyway, I think it's good method to learn. Good. I think pretty good. And what we can any more question or then we hope to meet you. I hope meet you next time in 2 weeks anyway. And see you. Yeah.
Okay.
And you so you'll be picking up on I don't know, I didn't get it.
That's not easy.
What will you be doing 2 weeks from now exactly?
I mean, Fulton will talk about nonlinear shooting on finite interval, that paper next time.
Okay.
Yeah. You may focus on that, reading that, you may get a better understanding.
Yeah, sure. I was hoping to get into like, applications and,
Application, you can use the method for whatever problem. If you look at some other, for example, your biology problem, then you can learn how to raise the boundary condition to guarantee the existence of solution. Sort of things you can analyze by using this method. This method
they cover a whole lot of stuff. Yeah,
I think Witten method, what the Witten method do modulation. I mean, because the model actually is just approximation to the real world wave, to the real wave. So we have to modulate it. We have to do the perturbation. How to modulate? How to perturbate it? So they use some kind of slow variable model scale perturbation. Use the Lagrange formulation to present the equation. Then you can, starting from Lagrange, because Lagrange tells you symmetries, conservation laws. So then you can, based on this, to exploit property of the solution. This is Wissen's work. And here, Fokas' work present the solution by using initial and Cauchy data, Cauchy data and boundary data.
If you are good enough, you can combine these two.
Yeah, definitely you can compare these two, because
What?
once you get the Wissem equation, then you can solve. This is a coupled equation. I should say Wissem equation creates some integral coupling. I really understand. If Gina gives us a talk at the end of this semester, then you can ask some question. They just present the integral coupling. So I realize this gives us some motivation. This gives us some conviction. Really, intercoupling is very, very important. Intercoupling is very important. Only intercoupling, if you get an intercoupling system, then you can get a solution. Otherwise, no way you can get exact solution to the nonlinear partial differential equations. No way, really, very hard. So solid solution is one of the class we can present so far. And another class we are doing actually is a lump solution, which is beautiful. We can use Maple to present beautifully. So definitely two very systematic classes of solution we can present by using Maple. One is soliton exponential type solution, and the other is rational function solution. We can present beautifully. They are all analytic in the whole xt plane or xyt space. Good. Yeah, good. Anyway, gradually you will learn. And if you got a question, write me email. Anyway, I can maybe give you some better explanation about your problem, sort of things. Anyway, we still can communicate each other with email. Good. Okay. I see you, everybody.
Okay.
I stop anyway recording. Okay, so then. Okay, good.
Thank you.
Stop this meeting. Yeah, thank you.